All right, it is 8, so we'll get started for today. So before I get into things, I just want to lay out the schedule for the rest of the semester, since last week is our last week, or next week is our last week, rather. I don't know about you, but that feels a lot shorter than 10 weeks. Maybe for you, it feels a lot longer than 10 weeks, but we're almost done here. So here is what I have planned for our next week. So today will be our regular lecture, but it's going to be our last lecture. So I put up a PowerPoint for today, and we're probably not going to get through it all. So the plan is, whatever I don't get through today, I'm going to record and put it up. So you will be responsible for that information. It probably would be like an extra 30 to 40 minutes as an additional lecture, but I'm going to put that up instead of going over it Monday. Monday will be a review day, with the caveat that I will be answering questions from people. And I've done this in the past where I've said, like, bring your questions and we'll go over them in class. And then when I come to class, nobody has any questions. So we're just staring at each other for like 5 minutes before somebody actually goes through their notes and thinks up a question. So I don't want to do that again. So the way we're going to structure this is that the way I'm thinking is that on Blackboard, possibly by message board, I don't quite know yet, but I'm going to set something up on Blackboard. And I want you to give me all your questions that you'd like me to go over for the final exam. That could just be, topics you want me to recover, specific questions, anything. And then on Monday, I'll go over those questions. If I don't have any questions, then I guess we won't do a review then. So make sure you have your questions. That being said, on Monday, it's not mandatory to be there, but we still do have a reading guide for Monday, so I'd still like you to do that. The reading guide, it's still due. The final is cumulative. Yep, sure is. Everything we've covered is fair game, and you'll see it on the final exam. Then on Wednesday, next week, since the university, for whatever reason, does not want to publish final exam schedules, I guess they're just going to leave it up to us to decide when the final exams are. So next Wednesday is the final exam. And I will leave this open. It will open at 12 a.m. on Wednesday and close on 11:59 p.m. And since this is the final, you will have 2 hours to do it. So you can take it during any time in that window. Regular rules apply in that it's open note. However, don't post anything online. If I find stuff online, you will get an automatic 0, and then you'll fail the class. So don't do that. Since we switched homework platforms, there's no way to look at our previous homework assignments. No, there is not, because Wiley closed down the old platform on July 31st. So that's just offline. So we can't look at our old homeworks, unfortunately. Right. So any questions about the schedule itself? All right. Now I do want to go over this question from test 3 because like all but 2 or 3 of you just got it completely wrong. So let's go over some math. So I have a cell. Temperature of the cell is 300. Inside the cell, I have 50 millimolar chlorine. Outside the cell, I have 150 millimolar chlorine. The membrane charge is minus 20 millivolts, so the inside is negative 0.02 volts. What's the free energy for transporting 3 moles of chlorine into the cell? So I'm taking 3 molecules of chlorine, bringing them from outside to inside. R is a constant, and F is also a constant. So just plug it in, R, 8.314, temperature, 300, natural log, final minus initial concentration. Well, I'm going inside the cell, so my final concentration is 50, and I initially came from outside the cell, where it's 150, plus Z of A, that's the charge of our ion, so our chlorine is minus 1, multiplied by Faraday's constant, 96,485, multiplied by our membrane potential. Since we're going inside the cell, we're going to where it's negative, so it's minus 0.02. And then I have 3 molecules, so I have to do this whole equation and multiplied by 3. Negative 2431 joules. So yeah, definitely go over all the math we went over in this class. And today it's actually quite a math heavy day. But yeah, we need to know how to do math. We need to know how to do algebra. We need to know how to look at an equation like this. And you need to know what these terms mean and how to use them. All right. Just something at this level, I would expect everyone to be able to just smash out of the park reading an equation like this and just putting in the variables. So it's a little surprising how poorly we did that as a class. So I really want you to focus on reading equations, knowing what variables mean, plugging those variables in. All right. So that's the only problem that on the test we had as a class issues with. I did open up the test where you can look at your answers now. After class, I will put up the grades, like what percentage you got. So that'll be all up after Wednesday. Right. So with that, we have quite a bit to cover. And like I said, we're not going to be able to finish it all, so I'll have that extra video later today as well. I'll be making that. But let's get into our final section on mechanisms. Well, a final section on enzymes rather. And on Monday, we were talking about different mechanisms. So we talked about the lysozyme mechanism, and then we ended here talking about trypsin. Where trypsin is a molecule that's part of the class of serine proteases. And what serine proteases do is that they break peptide bonds. They chop up protein. So when you eat a steak, the thing that's going to be breaking down the protein molecules in that steak, well, that's different trypsins, or different serine proteases rather. And the last slide we talked about was this specificity pocket, where all these serine proteases cut after different amino acids. They break different peptide bonds based on what amino acid they're looking at. And the amino acids they cut after are all determined by the specificity pocket, where you line this pocket in the protein with different amino acids. Based on what amino acids you have, you bind different side chains. And what those side chains, after you have them bound, you cut. So scissile bond, what that is saying this is the bond that will be cut, that peptide bond. And it's all determined based on the specificity pocket. And what we're going to jump right into is, how do serine proteases work? How do serine proteases cut a peptide bond? So we're going to go over the mechanism of the serine protease now. So here we have asp, his, and ser. Remember, this is the catalytic triad. These are going to be the amino acids in the protein that are important for our mechanism. Note that his is neutral to begin with. Remember, histidine has a pKa of 6. So it can either be protonated or deprotonated rather easily. Asp, negatively charged like normal. Serine has this OH like normal. So the first thing that happens is when we have our peptide that we want to cut, we have a nucleophilic attack. So good old organic chemistry terms right there, where the histidine will take that hydrogen from serine. Again, pKa 6. Histidine can be charged, no problem. So it's the perfect amino acid to do this. The aspartic acid here, well, let me ask the folks here. From your knowledge of organic chemistry, we have aspartic acid over here. And if you look throughout the mechanism, aspartic acid is not interacting with any substrate molecule. It's not gaining a hydrogen. It's not losing a hydrogen. The whole time, it's just interacting with histidine. So why is it important that aspartic acid is here? What's it doing to speed up this reaction? Why is it part of the catalytic triad if it just hangs out? Anyone have any ideas on what the role of a negatively charged aspartic acid could be in this mechanism? What's it doing there? Why do all serine proteases have this asp? If it doesn't do anything, like it's not getting any atoms, why would it be there? And if you actually look in the words, I have aided by asp, but how? Anyone have any ideas about this? This is one of those critical thinking questions where can you combine everything you've learned about chemistry in this point in your career and synthesize it onto a new process? So got two answers there where we have it's with the H bond. Yes, so the hydrogen bond is important. And then we have some other people who were able to combine that, where it is helping to stabilize the histidine. Yes, so very good. We see aspartic acid here, and it's hydrogen bonding with histidine the whole time. It doesn't do anything else. What that does is that it allows histidine to take on this proton. It allows histidine to be positively charged more easily. It it's assisting with that. It actually like modifies the pKa, because if histidine is around a negative amino acid, it's more likely to want to be positively charged. So it has a easier time to take this hydrogen from serine because it's surrounded by something that's negative. It feels that negative charge. And if you feel a negative charge around you, the way to neutralize that is to be a positive charge. So it's affecting histidine's ability to take a proton, making it easier, which speeds up this reaction. So very good. So yeah, our first step here is just acid, or rather base catalysis, where we have histidine acting as a base to take that proton from serine. So that's a base right there. Should not write base right here because it's going to be doing something different. So it's acting like a base. And then our serine, with that free oxygen, is doing a nucleophilic attack on this carbonyl carbon to make our intermediate. All right, so one more pause here. How do enzymes speed up reactions again? Who can tell me how enzymes speed up reactions? What do they do to speed up those reactions? And another way to ask it, so I'm drawing an energy diagram here of uncatalyzed versus catalyzed. What does the difference in these lines mean again? Lower activation energy, that's correct. How do they lower activation energy? Let's take that one step farther. You're completely correct. They lower the activation energy of the reaction. How do enzymes lower activation energy? They decrease the energy required for the transition state. Yes, that's true. I would kind of like just word that slightly differently. They stabilize the transition state. But yeah, they do decrease the energy of the transition state. So what I want people to remember is that this is the transition state. And we're going to look on the next slide how we stabilize that. So just keep that in mind. Enzymes stabilize the transition state. And so we're going to see how we stabilize the transition state. But here we are. Once we're in our intermediate, now we're going to have some acid catalysis where the oxygen, since it has all these electrons, remember this from organic chemistry where you draw your electrons and they're going to come here to make a double bond. And then these electrons are going to grab that proton from histidine. So now histidine is acting like an acid. So already we have our histidine acting both as a base and as an acid and back-to-back steps. And you have another intermediate where you have already cut your peptide bond. So we're cut, perfect. The only problem is we still have part of the molecule in blue attached to our enzyme. So we have to get rid of that. And we do that via water. So our N-terminus is free to leave. It's not covalently bound to anything. So the N terminus actually leaves. The C terminus is bound to our enzyme. So water will come in at the same position that our N terminus was. And histidine is going to act like a base again, which leads to a nucleophilic attack by the water on the carbonyl carbon to make another tetrahedral intermediate. Basically the same type of molecule that was made in after the first step is made into the second last step. Then all we have to do now is we have to go back to our original configuration. So we need to get that histidine, or sorry, that hydrogen off histidine and give it back to serine. So that's happening. Then we need to break this intermediate. We have to break the C terminus. So we do that. And now we have a complete C terminus that pops off. And our enzyme is back. Serine has its proton again. Histidine is in its neutral form. Again, aspartic acid was just hanging out, making histidine gain and lose a proton easier. And that is the mechanism of basically every single serine protease there is. There's a lot of different serine proteases, but they all work with this mechanism with serine, histidine, and aspartic acid. And when you look at this mechanism, the big player here is histidine, right? Histidine takes on a proton, gives a proton, takes on a proton, gives a proton. It's just acting like an acid base over and over and over again. And again, it's perfectly suited for this because we learned of the pK of 6. So it has no problem taking on and donating a proton again. All right, so is there any questions or any clarifications with that mechanism? And I do have all the steps written out here as well. So when you go and look back on it, but just off the top of your head, was anything you got a little confused on, or is this is probably one of those things that you just have to digest for a while and then you'll have questions on it. But just off the top of your heads, any questions whatsoever? All right. So as I mentioned, the transition state is that tetrahedral intermediate. And to speed up reactions, enzymes will make the transition state, lower the energy of the transition state. And if you don't know what that means, so let me just write that again, lower energy of trans state. That means they make favorable connections, favorable interactions with that transition state. And so our transition state was that tetrahedral intermediate, which is shown down here. And the way we stabilize that is that in serine proteases, there's a spot in the enzyme called the oxyanion hole, because in our intermediate, we make this oxyanion. So we have a space that has 2 amines with the hydrogens pointing right at this hole that makes a perfect fit for this negatively charged oxygen. Because when that oxygen goes there, which will happen when we're in this tetrahedral conformation, it immediately forms 2 hydrogen bonds. So we are stabilizing the oxygen, the negatively charged oxygen in the enzyme. And we're actually kind of pushing our substrate to adopt this form, because you can see without the intermediate, this oxygen, which is still partially negatively charged, is right next to this oxyanion hole. It's right next to two potential hydrogen bonds. So it's going to be feeling that. It's going to feel that attraction of two hydrogens, two positive hydrogens just hanging out right there. And so it's going to want to go over there and interact with them. And so it's the enzyme is kind of giving a gentle push to this carbonyl carbon saying, come over here. We got two hydrogen bonds waiting for you. And the oxygen says, okay, once I form this new bond, I'll come over and hang out with you two hydrogens. And that's how we lower the activation energy. That's how we stabilize the transition state via the oxyanion hole. So that's how we speed up cutting peptide bonds in the serine proteases. And all serine proteases will have that oxyanion hole. Now, serine proteases, they chop up proteins. And so usually when you make them, rating your cells, they aren't activated yet. Because just think how terrible that would be if you're making this protein in the ribosome inside your cell. And as soon as you make it, it just goes around and starts eating all your other proteins. Because again, proteins don't have, like, they're not conscious, right? They don't have a will. They don't know what they're doing is bad. They just interact with things based on electricity and hydrophobicity, based on chemistry. And so if a serine protease, as it came off the ribosome, was active, it would just destroy your cell. So you don't want that to happen. So these enzymes that break down other proteins, when they're made, they're going to be made as inactive precursors. They are called Zymogens or proenzymes. And if you have acute pancreatitis, what that means is that you're actually making these digestive enzymes and they're turned on before they should be. So they're actually eating you. So that's what acute pancreatitis is. Your enzymes are eating yourself. Now for trypsin, which is one of the serine proteases we talked about, the zymogen is called trypsinogen. And the way that trypsinogen is turned on is through another peptidase, another serine protease called enteropeptidase. And what enteropeptidase does is that it will cut between lysine and isoleucine, amino acid 15 and 16. And it actually just cuts 6 amino acids from there. So when trypsinogen is in the location where it needs to be turned on, that's when it's going to go and interact with enteropeptidase. Enteropeptidase cuts leucine isoleucine. And once that is cut, you now have active trypsin. The real cool thing about this process is that once one molecule of trypsin is turned on, it can go and turn on all other trypsins. It can go and find this bond and cut. So it's like an on switch. As soon as you have one enteropeptidase, it will turn on one trypsin. That trypsin will go turn on another trypsin, and then it's chain reaction as all these trypsins will start turning on each other. And like I said, it's an on switch. It will just all come online. So that's how we can turn on these proteolytic enzymes safely inside the cell. We have mechanisms to ensure they aren't turned on prematurely. So any questions about those ideas that we have covered so far? All right. So what should you focus on from the series of lectures? Make sure you know those mechanisms we went over. Know how we stabilize the transition state, the oxyanion hole, and also for lysozyme, how we do that. Also know why that's important to stabilize the transition state. Also know what a zymogen is. Also know why trypsin isn't always active. So those are just some of the things to focus on. But with that, that's the PowerPoint from Monday. Let's get on to our last PowerPoint, which is all math. Ending on everyone's favorite subject. And our last topic is going to be kinetics of enzymes, speed of enzymes. Previously, we've only talked about the thermodynamics of enzymes, binding the transition state, lowering the energy, how that speeds up things. Now we're actually going to go how we measure the speed of enzymes. And we're going to learn it through Michaelis-Menten kinetics. Michaelis-Menten kinetics is a theory of enzyme speed that was developed in roughly the 1920s, 30s by Michaelis and Menten, and using work of a couple other scientists. And your book goes through an awesome mathematical description of how they got all their terms and how they got to the final equation. And it's really lovely to walk through. And I would suggest that you do that. However, for the test, you don't need to derive anything from me. Just a fun little story. When I was going to get my PhD, when you go to get your PhD, you have to go through an exam called qualifying exams, where basically you sit in a room with 5 PhDs and they ask you anything they want for like 2 hours. And their goal is to see how much you know and what you don't know. And so one of the questions I got was derive the Michaelis-Menten equation. The equation you're looking in the top left, I had no idea how to do that. So that was their only one little reservation for me. I had to show that I could memorize this equation for them. But for us, I just need you to know what that equation in the top left says and how to use it. So let's look at this equation. The framework that we're going to use to understand the speed of reactions is this equation, is that E stands for free enzyme. That is enzyme not bound to anything. S stands for free substrate. Substrate not bound to anything. And the enzyme and substrate can bind to make an enzyme substrate complex. So they're bound right now, they're interacting. And this has some speed, some rate that's equal to K1. A lot of the times I feel students, when they see speed or rate, like their heart rate goes up a little bit. They get a little panicky because they don't quite know what that means. I guarantee you, everyone knows what like a K1 means because you use it in your day-to-day life, right? What's the speed limit on a highway? Well, if you're inside the city, it's usually 65 miles per hour. That means it takes you 1 hour to go 65 miles. We use the same thing for K1. The K1 is like number of events per time. That's basically what K1 means. So E plus S combined to ES and has a certain speed with that. And we're also going to assume that this complex can break down back to the free enzyme and free substrate. So it can bind and it can unbind. Both of these have speeds, and their speeds are different. Going the forward is one speed, going backwards is another speed. Once you're in the complex, you can complete the reaction to make your product and back to free enzyme. Oops, free enzyme. So your substrate is going to be converted to your product and going to be released. This is not reversible. We're going to assume once we have our product, we can't go back to our substrate. Now, enzymes can generally go in reverse. So in real life, it probably could go in reverse from P to S. However, just for our discussion today, we're going to assume that's not the case. We're going to make an assumption, and our assumption says once you make a product, you can't go back. And that has a different speed with it as well, K2. So that's the overall equation we're using to understand kinetics. Enzyme plus substrate makes a complex. That complex can break down, or that complex can make a product. And to measure the speed, so this velocity. So to measure how fast a reaction is going, we're going to call that velocity. Like, that's basically number of product per a given time. So the amount of product you're making per a given time, that's your velocity. This O means initial. So this means you mix enzyme and substrate, and you just take the initial, you take the velocity at the very first time point that you can. You just measure that first velocity, and then you're done. You take that measurement. And this initial velocity, we're going to say is equal to this expression. So it's equal to Vmax, which is maximum velocity. So maximum velocity is how fast you can go. So for example, your car might have a maximum velocity of like 130 miles per hour. An enzyme also has a maximum velocity, the fastest it can possibly go. So initial velocity is equal to maximum velocity multiplied by substrate concentration. So free substrate concentration. How much substrate you have in your reaction. Divided by Km. So Km is called the Michaelis constant. And the Michaelis constant is the amount of substrate you need to go 1/2 your maximum velocity, right? How much substrate do I have to add into my reaction to go 1/2 my maximum speed? That's the Michaelis constant. Plus how much free substrate there is. So that's how we can measure initial velocity. Now, before I go on, did I lose people, or where did I lose people on that discussion of those two equations? Anyone a little confused, like not sure what I said? Just take a few seconds here to let you write all that down, let you digest that, let you ask any questions if there are questions. All right. So the first bullet point is basically explaining Km again. When the amount of substrate you have in your reaction is equal to this Km value, then you go 1/2 your maximum velocity. your initial velocity is Vmax divided by 2 or 1/2 Vmax. If your enzyme has a low value of Km, then it's easier for you to go your maximum speed, right? Because remember, Km is how much substrate I need to go half my speed. So if that number is low, I can go fast easily. If Km is high, it's hard for me to go 1/2 my maximum speed. I just need a lot of substrate to do that. And so it's very hard for me to get to my maximum speed. And that I'm just going to leave the bullet points for a second. If you could draw your attention to this table, I have some different values of Km. So let's look at fumarase. Has a Km of 5.0 times 10 to the minus 6, which is a very small number. It's 0.000005. While chymotrypsin right here has a value of 4.4 times 10 to the minus 1, or a Km of 0.44. So fumarase has a much lower Km than chymotrypsin. So it's easier for fumarase to reach its maximum velocity than it is for chymotrypsin, just because of that Km value. So there's a few other values we need to know. Kcat. Kcat is what's called turnover number. So that is how many reactions happen per unit of time. And Kcat is simply your maximum velocity divided by your enzyme total. So total enzyme in the experiment. So that's what ET is. And our last variable is Kcat, turnover number, divided by Km, Michaelis constant. This is catalytic efficiency. This is just telling you how good your enzyme is at making a product. And the most efficient enzymes are going to be what are called diffuse control limited if they have a catalytic efficiency of 10 to the 8 to 10 to the 9. So on this table, we have some of those enzymes. And what diffusion controlled limit is, what that means is that your enzyme works so fast, the slowest step of the mechanism is for the substrate to diffuse to your enzyme. Once the substrate goes to your enzyme, the reaction's already done. So the slowest part of that reaction is coming into contact with your substrate, for your substrate to move to your enzyme. Right, so if we look at this plot now on the bottom left, we are plotting initial velocities versus substrate concentration. I know that's cut off at the bottom. So I'm going to rewrite what these say. So you can see that the x-axis is actually labeled Km, 2 Km, 3 Km, 4 Km, 5 Km. That's actually a measure of substrate concentration. Because remember, when S, the amount of substrate equals Km, that's going 1/2 your maximum velocity. So Km is in units of substrate. It is substrate. You can see that in the table as well. Km, unit of molarity, moles divided by liters. And when you have this plot of initial velocity versus substrate concentration, for enzymes, you usually get a curve like this. As your substrate concentration goes up, your initial velocity also speeds up. And you can do, from this plot, you can determine what your maximum velocity is. And once you have your maximum velocity, you go to what 1/2 that number is. So for example, if our maximum velocity here was 10, Vmax divided by 2 would be 5. And once you have that, you take where your 1/2 Vmax is and you draw a line until you hit your curve. Once you hit your curve, you draw a line down to the x-axis. Whatever substrate concentration that is, that's Km. So from this plot of doing initial velocities for substrate concentration, you can determine Km. You can determine what substrate concentration you need to go 1/2 your maximum velocity. All right, so that was a ton of information right there on this one little slide. So any questions or clarifications anyone want to have on that information? Did I lose you? Just not sure of what I said. Feel free to ask. And if not, so let's see how well you retain that information then. Here I have a table of data. The first column is substrate concentration. Second column is initial velocity. I want you to tell me what Km is. So read this, and this is actually a very important skill for you to have if you're a science major. Read a table and tell me what the table says. So this is good training for that. So I want you to look at this table and try to get it. Once you have an idea what Km is, if you could put it in chat via a private message to me, that would be great. But I'm going to give you, like a minute or so. Look at this table. Try to tell me what Km is. And if you're having a little difficulties with this, the first question you should be asking yourself is, what is Vmax? And once you have Vmax, what's 1/2 Vmax? once you have a guess, please do send me a message. We'll do like a minute or so for this. It would help if I had my mic on, wouldn't it? All right. So the first thing we want to do is determine what Vmax is. So if we look at our table here, at 50 millimolar substrate, we're going 1120. Times that by 10, so we increase tenfold. We're not going that much faster, 1191. Increase that by tenfold, we don't speed up like at all, 1199. So roughly Vmax is 1200 millimolars per second. Doesn't matter how much substrate we add at this point, we're not speeding up. So that's Vmax. 1/2 Vmax would be roughly 600 millimolar per second. And Km is the substrate concentration. That's not a 5, that's an S. It's the substrate concentration that makes us go 1/2 Vmax. So how much substrate do we need to go 600? Well, if we look on the table, we have two values that are below. We have one value that's below 600, one's above 600. So 600 is somewhere between 3 and 5. And based on this, I would say, roughly 3.5 millimolar. That will probably get you 600. So Km, based on this data alone, is roughly 3.5 millimolar. Questions about that? All right. Here's a graph. The graph has an initial velocity on the y, substrate on the x. Same idea. What's Km? Again, once you have your answer, send me a message, but see if you can figure out what Km is based on this graph. I'll give you a couple minutes to do this as well. And if you have questions about this or are confused, please let me know as well. Just don't sit there in confusion and wait for me to give you the answer, because that is not how you learn. Remember, when you have an answer, when you have a guess, do let me know. Cough, participation points, cough. All right. So let's look at how we find Km from a graph. Same idea. First things first, find Vmax. So what is Vmax? Well, this line is still going up, still going up. So we can assume that this line will probably go something like this for a while before leveling off. So I'm going to say Vmax is roughly 5. If you said something like 4.5, yeah, that's fine. It's definitely not 4. And it's definitely not like 4.25 because it's still going to be going up. So I just said, somewhere around 5 is probably not a bad guess, which means 1/2 Vmax is roughly 2.5. So roughly right there. Then once you have that, you draw a line over until you hit your curve, and then you draw a line down. So Vmax is a little bit above 1, like 1.1 maybe, something like that. And that's how you find, or sorry, did I say Vmax? I meant Km. Km is like 1.1. So that's how you find Km through a graph of initial velocity versus substrate concentration. Questions about that idea? All right. So let's do a little bit more math then. So I have an enzyme that has a maximum velocity of 2.68 molar per second. And I run an experiment, and my initial velocity is 1.25 molar per second. And my substrate concentration is 0.22, and my total enzyme concentration is 0.34. So I want you to tell me what Km, Kcat, and catalytic efficiency is. So again, I'll give you a few minutes to do that. And I'm going to put up a poll here as well as a question timer. So let me know if you finished incompetent, finished but not sure, got part way not sure, or yet no idea how to begin. And someone already put finished but not sure after 15 seconds. So I'm guessing you just moved on from question 2. All right then. But yeah, take a stab at this. We'll do a few more minutes with this, or maybe like one more minute as we have the majority of people done. All right, since we have all answered, looks like well, we finished, maybe not confident, but most of us finished. So let's take a look at this, and did not mean to do that. So the first thing we need to do is figure out, well, the first thing we should do is label our numbers. So enzyme has a maximum velocity of 2.68. So Vmax 2.68 molar per second. If I run an experiment with initial velocity, so that's V naught, 1.25 molar per second, with a substrate concentration, so that's S, it's 0.22 molar, and total enzyme concentration, that's E total, 0.34 molar. So this is what I would suggest when doing problems like these. Just pick out the numbers, write what they are using your variables. Makes these equations a lot easier to use. So the first question is, what is Kn? So I have a V naught, I have a Vmax, and I have a substrate. So I can figure out Km by doing a little bit of algebra. So the first thing I'm going to do is multiply each side by my denominator here. I get initial velocity multiplied by Km plus substrate concentration equals Vmax multiplied by substrate. So I'm going to divide each side now by my initial velocity. So I get Km plus substrate equals Vmax multiplied by substrate divided by initial velocity. And since I'm solving for Km, I want that alone. So I'm going to subtract each side by substrate. I'm going to draw an arrow over here. Km equals Vmax multiplied by substrate divided by initial velocity minus substrate concentration. So that's how we can use algebra to rearrange our equation, solve for Km. And let me just plug in the values. Km equals Vmax 2.68 multiplied by 0.22 divided by 1.25 minus 0.22. And that means Km is 0.252 molar. When I solve for that, double check my math. 2.69 times. Yep, that's Km. Now we need to do Kcat. Well, Kcat's easy. It's Vmax divided by enzyme total, and we already have those. So Kcat equals 2.68 divided by 0.34. And that's 7.881 over seconds, because this is meters over seconds. And this is not meters, molarity over seconds divided by molarity. So the units are 1 over seconds. And catalytic efficiency is Kcat divided by Km. So Kcat is 7.88. Km is 0.252. My catalytic efficiency is 31.3. 1 over, this is a weird unit, 1 over molar seconds. So any questions about anything so far about Michaelis-Menten kinetics? All right. Now, when scientists were first doing enzyme kinetics, they would get plots like we looked at, like down here in the bottom left, where you have a curve. And as we just saw for this problem, to get Km, you kind of have to guess what Vmax is. Like we said, it's like 5. And guessing like that isn't the greatest thing when it comes to science. You want to be more precise than that. You don't want to say, Vmax is probably this. And back in the days of early enzyme kinetics, you didn't have computers and you couldn't like do an equation to fit this curve easily and get variables. Like Excel can do this, no problem now. Back in the 50s, back in the 40s, you didn't have a computer to do that. So to figure out Km and Vmax from experimental data, you would make what's called a Lineweaver-Burk plot or a double reciprocal plot. And this plot can allow you to determine Vmax and Km and not be ambiguous about it, like not make any assumptions or guesses. And to make a double reciprocal plot, you do 1 over your initial velocity on the y, 1 over substrate on the x. So it's the opposite of what we were looking at. We were looking at initial velocity versus substrate concentration. Now we're looking 1 over velocity and 1 over substrate. And when we plot our data like this, the cool thing that comes out is that the y-intercept, where the line crosses y, that's 1 over Vmax. Where the line crosses x, that's negative 1 over Km. So for example, if this number was 10, if we cross the y-intercept at 10, what we're saying is 1 over Vmax equals 10. So to find Vmax, you just flip the fractions. So this Vmax goes on the top, the 1 goes on the bottom. This 1 goes on the top and the 10 goes on the bottom. Remember, if I say like a whole number like 10, or if I say any number, you can take any number and divide it by 1, and you will get that number back again. So that's why I have that 10 divided by 1. So if our y-intercept was 10, our Vmax would be 1 over 10, or 0.1. Conversely, for our Km here, if we cross the line at -6, right? If this value was -6, what we're saying is -1 over Km equals -6. So I'm going to do the same thing here. And -Km, I'm going to flip the fractions. -Km equals -1 over 6. And these negative signs cancel out. So Km is actually 1 over 6. So this is how we can use what's called a double reciprocal plot to figure out the values of Km and Vmax for our enzyme. So, of course, let's have some practice. Here's a Lineweaver-Burk plot. What's Km and Vmax? Let me put up that question timer again as a way to gauge where people are at. I'll relaunch that poll. So let me download it first. Okay. So question pulls up again, same idea of let me know where you're at. If you have questions, feel free to put them to me as well, but I'll give you a couple minutes to get comfortable with a double reciprocal plot. do about 30 more seconds of this. All right. Download that. So y-intercept is 1 over Vmax. X-intercept is -1 over Km. So let's say this is 1.8. So Vmax is equal to 1 over 1.8, which, I'm gonna get out Excel to tell me what that is. 0.55, 555, 555, 55. 555. So 0.55 repeating. This, I don't know, let's say that's -2.7. So Km is equal to 1 over 2.7, which is 1 divided by 2.7. 0.37. That's Km and Vmax from the line we revert. Questions about that? All right. Now we're going to step away from pure kinetics here and just talk about kind of the general mechanisms we see for enzymes. So we're going to talk about bi-substrate reactions here. And bi-substrate reactions are reactions that use 2 substrates. And so 60% of all the reactions we know for enzymes use 2 substrates. And for Michaelis-Menten, we were talking about 1 substrate S. So we're making it a little more complicated here, where instead of S, we have 2 molecules. And our general reaction for this is substrate A plus B will make products P and Q. And another way we can do that is here we're showing the same thing happening, where we have 2 substrates, the compound PX plus the compound B, and we're just switching the covalent bond to make P by itself, and now the complex BX. So both of these are bi-substrate reactions. And for bi-substrate reactions, there are only a couple of ways that they happen in nature. And the first is called a sequential reaction. And a sequential reaction says, for a reaction to happen, you need both substrate bound first. So all substrates, or in this case, both substrates, have to be bound to the enzyme before your reaction happens. And there's 2 ways you can do this, ordered or random. What an ordered sequential reaction says is that one substrate must always bind first before the second substrate does. So here, A always binds first, followed by B, and then P will come off, followed by Q. And a random sequential reaction says that the substrates and products can come on in any order. So either A comes on first or B comes on first. It doesn't matter. And then either P comes off first or Q comes off first. It doesn't matter. So sequential, both substrates need to bind. Ordered, they have an order. random, they don't. It doesn't matter what order they come on. And that's different than a double displacement reaction or a ping pong reaction. In a double displacement reaction, only one substrate binds at a time. So here we have A coming on, and when A comes on, we make product P. Now, one thing that's confusing here is that we have these E and F. What F is saying is that enzyme E has been modified to become enzyme F. And we've already seen this idea of modification, like when we were looking at the chymotrypsin mechanism at the very beginning of class today. So for there, we were having our serine bind to the C terminus, and histidine was positively charged. That would be like enzyme F here, where E is modified in some way to become slightly different. So substrate A comes on, and the product comes off, and now we have the modified version of enzyme E, which we're calling enzyme F. Then B can come on now that F is there, and that will bind with F and make product Q, and the enzyme is back to its normal configuration. And then we start over again where A can bind again, and we just repeat. And so this is called double displacement or ping pong, because it comes on, comes off, comes on, comes off, ping pong, ping pong, substrate product, substrate product. So those are the two different ways in which a bi-substrate reaction can happen. It can either happen via a sequential reaction, everything binds, or a double displacement reaction where only one thing binds at a time. So any questions about those definitions of the type of bi-substrate reactions? All right. So let's see if we understand this. So let's say we have a bi-substrate reaction, and we have some product P. And so in my reaction mixture, so I'm gonna have this in a beaker, right? So I have P that is labeled somehow, that I can determine its labeling, it's being labeled, right? So it's either fluorescent or it's radioactive, it's somehow labeled. And I put that in a test tube with enzyme E and substrate A only. So I want to know, would this produce A with the same type of label if this followed ping pong and no B, Q, or F is present? So think about that for a minute. Would we create A? And let's see. I just created a poll for this. A lot easier to do that in Zoom. So will we create A star? Yes or no? And just so you know, we're going to assume our reactions can go reversible. So we're going to say all these steps here, in theory, are reversible. Do about 20 more seconds for this. All right. Oops. So let me download those results. So the answer here is yes. And the way that this happens is that to make A, we need enzyme F. Because product P only binds to enzyme F. However, in our experiment, we don't have any enzyme F. So we can't go directly from labeled P to labeled A. However, I did say that this does happen. So the way it happens is that we do have enzyme E and A and substrate A. So E and A can combine to make enzyme F plus unlabeled P. And if we have enzyme F around, enzyme F can interact with that labeled P in reverse to make labeled A plus enzyme E. So yes, as long as we have A and E to start with, we can make P. Now, if I ask this question and I didn't have this A here, and I said we had labeled P and enzyme E, is it possible to make labeled A? The answer there is no. Because to go backwards, I need this enzyme version F. However, since we do start with substrate A, we can make enzyme F, and then enzyme F can interact with enzyme or substrate P and go backwards. So questions about that logic? All right. So same idea here. So I have a reaction and it's bi-substrate. Again, I have P and I have A and I have E. I want to know in this reaction why make labeled A. So same idea. Let me put the poll back up and see what you think about this. Using bi-substrate reaction where we're having sequential, can we make A here? And we'll do about 20 more seconds for this one. All right. And that, save it. So here, the answer is no. We cannot make A because this is, so this can also go in reverse. However, in a sequential mechanism, to go forward, I need both A and B present. To go backwards, I need both P and Q present. Since I don't have B or Q, I can't go in either direction. So actually, with these three molecules, no reaction whatsoever would happen. No chemistry would happen. They would just sit in the water and not do anything. So, no, you would not make A because no reaction would happen. Any questions about that idea? Right. Now, let's see. Just taking a look here. Right. So I think this, the next series of slides are all connected and talking about inhibitors. So what I'll do is, since there's only a few minutes left, I'm going to call the live lecture here. This afternoon, I'll record these slides, and I'm going to put it up, and you'll find it. You'll find that section of the lecture in the folder for today. So it would be in the August 4th folder, and it will be called like lecture part 2, where I'll just go over enzyme inhibition. I will also, this afternoon, set up a way in which you can have your questions ready for Monday. Just as a reminder, Monday is going to be a review day. Please submit your questions before Monday at 8, and we'll go from there. I'm going to put up one last homework that'll be due next week, Wednesday. It's going to be on our new site. That'll be the last homework of the semester. If you have any questions, please don't hesitate to reach out. Otherwise, you are done for the most part, other than this enzyme inhibition, of learning new information for biochemistry semester 1. So hopefully you've learned some interesting things. Hopefully you look at life a little bit differently now that you have some understanding of all the bits and pieces that go into it. But yeah, thank you for sticking with me for these, well, 9 weeks, 10 weeks next week. And hopefully I'll see you on Monday for that fun review session. Otherwise, I don't have anything left for you. So I hope you have a good weekend, and see you on Monday. Take care, everybody.